Hey guys, welcome back. In this video, we're going to talk about polyprotic acids. Right? What is a polyprotic acid? This is an acids with more than one. Dissociable proton, or H plus. All right. That, there's H2CO3, H2SO3, H3PO4, etc. There's more. All right. So if I look at these, typically Ka1, which would be the first proton, is going to be larger than Ka2, which is our second H plus, which is larger than Ka3, etc. Right? It just goes on and on and on. Right? However many there are. Okay. So, for example, we have sulfuric acid. We'll have Ka1, and that would be H2SO3 in solution, plus water, going to hydronium and hydrogen sulfide. Ka1, the expression would be your hydronium, your hydrogen sulfide, all over your acid, sulfuric acid. Now, Ka1 happens to be 1.3 times 10 to the negative 2, where I looked it up at. And we have Ka2, and so that would be, now, after step 1, right, we have our acid and our conjugate base. However, our conjugate base can be an acid as well, HSO3 minus, hydrogen sulfide. Can further react with water in the second step, so each of these is a step, to get more hydronium and sulfite. So Ka2's expression still has hydronium in it. We're still an acid. Now we got sulfite. And we have bisulfite, or hydrogen sulfite. And Ka2 for us is 6.3 times 10 to the negative 8. All right. And if you notice, that's a million times less of a number. All right. So what will we do with this? Well, let's do an example. All right. Let's do an example. And that is, what is the pH and concentration of all species in a 0.10 molar solution of phosphoric acid? That's a great question. All right. So we need to, first of all, what is phosphoric acid? Well, it comes from phosphate, so it has H3PO4, and it's going to have 3 Ka values. Ka1 is 6.3 times 10 to the negative 3rd. Ka2 is 6.3 times 10 to the negative 8. And Ka3 is 5.0 times 10 to the negative 13th. Let me make sure that's right. Oh, there we go. So, yeah, negative 8. 6.3, negative 3, negative 8. Yes, all right. So now, we're going to look at Ka1 first. First proton, H3PO4 plus H2O goes to what? Well, we've got hydronium, right? It's an acid. That makes sense. And then phosphoric acid has to lose a proton, so you'd have H2PO4 minus. Ka1 would be equal to the concentration of hydronium, dihydrogen phosphate, all over phosphoric acid. All right, ice table. So we start off with 0.10 molar. Don't care. None and none. Change. Minus X plus X plus X. All right. So at equilibrium, I have 0.10 minus X, X, and X. Plugging in. So we have 6.3 times 10 to the negative third equals X squared all over 0.10 minus X. All right. Well, I don't think I'm going to approximate here because the difference between this is not 1,000. So I'm going to bring it up. Right? We're going to bring this up here. And so we got 6.3 times 10 to the negative 4 minus 6.3 times 10 to the negative third X equals X squared. So that means 0 equals X squared plus 6.3 times 10 to the negative third X minus 6.3 times 10 to the negative 4. So if we do this, X would equal, let's see if I go to my calculator. Yes. We have, 3 times 10 to the negative third there. And negative 6.3. I get... Yeah, I get 0.022 for X. Now that's the first ionization, which is fantastic. So I know what X is. However, there is a second ionization, and I'll do that in blue. All right, where we have H2PO4 minus plus water, going back and forth with hydronium again, and now it's just hydrogen phosphate. Ka2's expression, hydronium, hydrogen phosphate over dihydrogen phosphate. All right. So now ice table. Originally now we have concentrations. The concentration after the first equilibrium of hydronium and dihydrogen phosphate is X. So X goes here and X goes there. I'm going to keep the same color for X. So I have 0.022 molar and 0.022 molar. And nothing, we're not worried about water. The change minus, now I would not if you use X, it's okay, but I recommend a different character than X. I'm going to use Y. You can use a Greek letter, you can use all sorts of things. It does not matter to me. You might want to use like gamma. I don't care. Something that is not the same. So Y for me, I have to be careful with, because sometimes my Y's, if I write them fast, look like X's. So what I'm going to do is actually not use Y. I'm going to do this. Use gamma. Why? I don't know. I'm just using gamma. So at equilibrium, I have 0.022 minus gamma, 0.022 plus gamma, and gamma. All right. So now using, just like we did in the first one, we're using like this expression. This expression went right there. So this expression is going to come right here. Ka2, which is 6.3 times 10 to the negative 8, equals 0.022 plus gamma, gamma all over 0.022 minus gamma. All right. Now, these gammas in blue. Because our change is so small, right? We have, what do I mean? This is negative 8, and that's negative 1, 2. 10 to the minus 2. So it's 10 to the 6 times difference, right? So if you had $1 million in the bank, you wouldn't worry about going out to lunch. I guess there's places where you would. I'm sure there's fancy restaurants that I've never been to or probably will. But most of us wouldn't worry about going to McDonald's, right? Or wherever. So the change here is negligible. So we can approximate these to 0. And so to do that, I'm just going to 0, 0. All right. So this is approximately equal to 6.3 times 10 to the minus 8 all over 0.022 all over 0.022 times gamma. So that means what? That means 6.3 times 10 to the minus 8 equals gamma. All right. But that's just 2. What about 3? So for the third proton, right, I have HPO4 minus plus water going to hydronium and phosphate. So this Ka3 will be equal to hydronium, phosphate, all over hydrogen phosphate. All right. Ice table. Now, here is what we start with because that's what we ended with, right? So for hydrogen phosphate, we are going to start with 6.3 times 10 to the negative 8. For hydronium now, we have X for hydronium up here, right? So if I scroll back up, there you go. And you have this. Well, what is 0.022 plus 6.3 times 10 to the minus 8. I think it's 0.022, right? 1, 2, 3. You got a bunch of zeros before you get to the 6. So we're going to just keep 0.022. And then nothing. Minus, I'm going to put z down, plus z, plus z. So we have 6.3 times 10 to the minus 8 minus z, 0.022 plus z, and z. All right, so Ka3, which was 5 times 10 to the negative 13th, is going to equal 0.022 plus z, z all over 6.3 times 10 to the minus 8 minus z. All right, the only z we need to worry about is this one. Why? Because we can approximate the other ones, right? Because negative 13, negative 1, 2, that's a big difference. We can approximate that to 0. And then, again, that's negative 8 and 13, still a huge difference. That's 0. So we're going to approximate this to 5.0 times 10 to the minus 13 equals 0.022 times z all over 6.3 times 10 to the minus 8. All right, so let's do the math. 5 times 10 to the negative 13 times 6.3 times 10 to the minus 8 divided by 0.022. I think I did that right. And I got 1.4 times 10 to the negative 18th. Which is really, really, really small. All right, so now we have all of our numbers. What are all the species? Well, we have H3PO4, phosphoric acid, H2PO4 minus, HPO4 3 minus, PO4, I messed up there, sorry about that. Let's try that again. PO4 2 minus, 3 minus, there we go. H3O plus, which means we have OH minus, and then we're going to have a pH. All right, so we got all these concentrations to work out. All right, so if we look at the first one, hydrogen phosphoric acid, was 0.1 minus X. So if I write that out, 0.10 minus X, well, X is, so let's write these out. X is 0.022. Blue was gamma. Gamma is 6.3 times 10 to the minus 8. And Z was 1.4 times 10 to the negative 18. Which is really small, but that's okay. All right, so 0.1 minus 0.022, we get 0.078. So I get 0.078 molar for phosphoric acid. Dihydrogen phosphate is X minus gamma. X minus gamma. And gamma, that we just did that over here, right? We just did that right here. Well, we did it plus, but minus is the same thing, right? And so that's just going to be X of 0.022 molar. Hydrogen phosphate is gamma minus Z. Which is this gamma, which is 6.3 times 10 to the negative 8 molar. Phosphate is Z, which is 1.4 times 10 to the negative 18 molar, which not many of those in solution. Hydronium is going to just be X, all right? That's going to be the case for most of the time, 0, 2, 2. All right, so hydroxide would be Kw over X, right, which is 1 times 10 to the negative 14 divided by 0.022. And so 1 times 10 to the negative 14 divided by 0.022. I get 4.54 repeating, so 4.5 times 10 to the negative 13 molar. And the pH is negative log of X in this case, which is the negative log of 0.022. I get 1.657, so let's call it 1.7. And that would be a polyprotic acid problem. Hopefully that works. If you have any questions, let me know. Otherwise, we'll see you next time, guys.